The universe is vibrating. Not in a poetic sense, not as a metaphor for the way cosmic events ripple across space. Literally vibrating. A physical oscillation in the fabric of space-time itself. A wave so low in frequency that a single cycle takes years to complete, washing through everything that exists, passing through you right now as you read this, bending the space between atoms in your body by an amount so small it has no name in ordinary language. It has been doing this since before our sun existed. We heard it for the first time in 2023. The detection was made not by a single telescope, but a collaboration of radio observatories across 4 continents, listening to the most precise natural clocks in the universe, pulsars, rapidly rotating neutron stars that emit radio beams with a regularity that rivals atomic clocks, and finding in the tiny deviations of their timing the signature of something that had been moving through the universe for billions of years without anyone detecting it. A background hum. A gravitational wave so pervasive, so fundamental, so woven into the structure of space-time itself that it is not produced by any single catastrophic event. It is produced by all of them, everywhere, across the entire history of the observable universe, simultaneously. The universe does not just contain gravitational waves. The universe is filled with them, saturated with them. And what we heard in 2023 was not an event. It was the background, the baseline, the permanent gravitational noise floor of a cosmos that has been colliding and merging and consuming itself for 13 billion years. A heartbeat, slow, deep, and very old. To understand what was detected, you need to understand what gravitational waves are and why hearing a background of them is different from anything we had done before. When LIGO detected gravitational waves for the first time in September 2015, it was listening for a specific event, the merger of 2 stellar mass black holes approximately 1.3 billion light-years away. The merger lasted a fraction of a second. The signal was a brief chirp, a rising frequency, a peak, a ring down that passed through the detector in less than a second and was gone. That detection was extraordinary. It confirmed Einstein had made a century earlier. It opened gravitational wave astronomy as a field. It was by any measure one of the greatest scientific achievements of the 21st century. But it was a single event, a discrete signal from a specific source at a specific moment. What the Nanograph collaboration and its international partners detected in 2023 was something different in kind. Not a single event, not a chirp, a background, a continuous, isotropic, stochastic signal present in every direction at all times. A gravitational wave background that fills all of space the way the cosmic microwave background fills all of space. Not arriving from one direction, but arriving from everywhere, simultaneously. The accumulated product of an enormous population of sources distributed across the observable universe. A hum, constant, pervasive, old. The instrument used to detect it is one of the most elegant in science. Pulsars are neutron stars, the collapsed remnants of massive stars that emit narrow beams of radio waves from their magnetic poles. As the neutron star rotates, those beams sweep across space like a lighthouse. When the beam sweeps across Earth, we detect a pulse. The rotation rate of a pulsar is extraordinarily stable. Millisecond pulsars, the fastest type, complete hundreds of rotations per second and maintain that rate with a precision that loses less than a microsecond per year. They are effectively natural atomic clocks distributed across the galaxy. If you monitor a pulsar's timing over years and decades, you can predict when each pulse should arrive at Earth with extraordinary precision. Any deviation from the predicted arrival time, any pulse arriving slightly early or slightly late, indicates that something has changed between the pulsar and the detector. A gravitational wave passing through the space between a pulsar and Earth stretches and compresses that space. When the wave stretches, the pulse arrives slightly late. When it compresses, slightly early. The deviation is tiny. We are measuring changes in the arrival time of radio pulses at the level of nanoseconds, billionths of a second, over baseline distances of thousands of light years. But pulsars are stable enough to make those measurements meaningful. A pulsar timing array uses dozens of pulsars simultaneously, monitoring all of them continuously, comparing their arrival time deviations against each other. A gravitational wave background produces a specific pattern of correlations between pulsars at different positions in the sky. Two pulsars close together in the sky show arrival time deviations that are strongly correlated. They both feel the waves similarly at similar times. Two pulsars at right angles show a weaker correlation. Two pulsars in opposite directions show a specific correlation that is weaker still, but non-zero, following a mathematical relationship called the Helling-Downs curve. In 2023, Nanograph, the North American Nanohertz Observatory for Gravitational Waves, and 3 independent international collaborations announced simultaneously that they had detected this pattern, the Helling-Downs correlation, the specific signature that only a gravitational wave background can produce. Not a candidate signal, not a marginal detection, a clear, statistically robust, independently confirmed signal in multiple datasets from multiple telescopes, analyzed by multiple teams using multiple methods. The gravitational wave background is real. We are inside it. We have always been inside it. Now here is the question that every person who understands what was detected immediately asks.
What is producing it? The leading explanation is supermassive black hole binaries. At the center of almost every large galaxy in the observable universe sits a supermassive black hole, objects millions or billions times the mass of our Sun. When two galaxies collide and merge, which happens frequently on cosmic timescales, as galaxies are drawn together by gravity and the universe's large-scale structure, their central black holes eventually sink toward each other through a process called dynamical friction. They form a binary system, two supermassive black holes orbiting each other, separated by a distance that shrinks over millions of years as they lose energy to gravitational radiation. As they spiral inward, they produce gravitational waves. Individual supermassive black hole binaries produce gravitational waves at low frequencies, frequencies in the nanohertz range, periods of years to decades, far too low for LIGO, which is sensitive to frequencies hundreds of times higher, but exactly in the range accessible to pulsar timing arrays, which monitor their pulsars over years and decades. There are an estimated 100,000 to 1 million supermassive black hole binaries in various stages of in-spiral across the observable universe at any given time, each one producing gravitational waves. All of them, together, summed across the full observable universe, produce an incoherent background. Waves arriving from all directions, at all phases, averaging into a stochastic hum that fills all of space. The gravitational wave background detected in 2023 is consistent with this explanation. But consistent with is not the same as confirmed, because there are other possible sources of the gravitational wave background, and they are stranger. The Big Bang itself was not a quiet event. In the first fraction of a second after the beginning, the universe underwent processes of extraordinary violence, phase transitions, the separation of fundamental forces, possibly a period of extremely rapid accelerated expansion called inflation that could have produced gravitational waves. waves generated in the first moments of existence, propagating through the expanding universe for 13 billion years, still present today as a primordial background woven into the structure of space-time. Primordial gravitational waves from inflation were predicted by Alan Guth and other architects of inflationary cosmology. Detecting them would be direct observational evidence for inflation, confirmation that the universe underwent the extremely rapid expansion in its first fraction of a second that explains the large-scale uniformity we observe today. The gravitational wave background detected in 2023 could contain a component from this primordial signal. Currently, the data cannot cleanly distinguish between the supermassive black hole binary explanation and a primordial contribution. The signal is too young. We have only a few decades of pulsar timing data, and the gravitational wave background has a frequency structure that requires longer baselines to fully characterize. Future decades of observation will sharpen the measurement. But the possibility that what we heard in 2023 is partly the echo of the Big Bang, gravitational waves born in the first moments of the universe, finally detected by an array of neutron star clocks scattered across our galaxy, is real. It is not a fringe possibility. It is one of the leading interpretations of a confirmed detection. There is a third possible source that the physics does not rule out, and that produces a specific pattern of gravitational waves different enough from supermassive black hole binaries that future observations might distinguish them. Cosmic strings. Cosmic strings are one-dimensional defects in space-time, hypothetical relics from phase transitions in the early universe, where regions of space that had been in different quantum states during the rapid cooling of the Big Bang were joined by boundaries. Think of them as cracks in the fabric of space-time, stretched across cosmic distances, vibrating and oscillating, and occasionally intersecting and reconnecting. They have never been directly observed. There is no confirmed cosmic string in any dataset. But cosmic string networks produce gravitational waves. Oscillating strings lose energy to gravitational radiation. The superposition of this radiation across a cosmic string network, if such a network exists, would produce a gravitational wave background with a specific spectral shape that differs subtly from the supermassive black hole binary prediction. If the continued characterization of the gravitational wave background over the coming decades reveals a spectral shape that does not match the binary black hole prediction, cosmic strings become a candidate explanation. Their detection would be the first direct evidence for a class of topological defect in spacetime, a remnant of the quantum structure of the early universe preserved in the gravitational signal washing through everything right now. Here's what the detection means for the physics we use to understand the universe. Einstein's general relativity predicts gravitational waves. We have now confirmed them in two completely different frequency bands, the 100 Hz range probed by LIGO and the nanohertz range probed by pulsar timing arrays. The physics is consistent across 7 orders of frequency. The same framework that describes the gentle curvature of spacetime near Earth describes the violent mergers of black holes and the background hum of a cosmos full of colliding galaxies. But the gravitational wave background also opens a new window, a window into processes and epochs that no electromagnetic observation, no light, no radio waves, no X-rays can access.
The cosmic microwave background, the oldest light we can detect, was produced 380,000 years after the Big Bang. Before that, the universe was opaque to electromagnetic radiation. Photons could not travel freely through the hot, dense plasma of the early universe. Our electromagnetic view of cosmic history has a wall at 380,000 years. Gravitational waves do not have this wall. They interact so weakly with matter that they pass through the hot plasma of the early universe without scattering, without absorption, without any of the processes that blocked light. A primordial gravitational wave background carries information from before the cosmic microwave background, from the first seconds, the first fraction of a second, from epochs we currently cannot see with any instrument and may never see with any electromagnetic telescope. If the gravitational wave background contains a primordial component, it is a window into the first moments of existence. We are not just listening to the universe's past, we are listening to its birth. What does the signal sound like? The gravitational wave background detected by pulsar timing arrays is at frequencies of approximately 1 to 100 nanohertz, 1 to 100 billionths of a cycle per second. A single cycle of the dominant frequency takes approximately 3 to 30 years to complete. This is far below any sound the human ear can detect. The lowest note audible to most people has a frequency of approximately 20 cycles per second. The gravitational wave background is roughly 10 billion times lower in frequency than that. Converting it to audible sound, as NASA did with the Perseus black hole in the acoustic sonification story you may have seen on this channel, requires shifting the frequency up by many orders of magnitude. The resulting sound, when this has been experimentally done, is a deep, slow, rhythmic pulse, a throb, a beat so slow it barely qualifies as sound in any human intuitive sense. A heartbeat. The analogy is imprecise. A heartbeat is periodic, regular, produced by a single source with a fixed rhythm. The gravitational wave background is stochastic, irregular, produced by an enormous population of sources, a superposition of millions of individual waves from different directions and different moments in cosmic history. But the analogy captures something real, a persistent, low-frequency oscillation in the medium that fills all of space, a signal that has been present as long as the universe has contained merging galaxies and colliding black holes, present before Earth formed, present before the Sun ignited, during every moment of the 4 billion years of life on this planet. We just didn't have the instruments to hear it. There is something specific about this detection that separates it from every other discovery discussed on this channel. The gravitational wave background is not far away. The oh my god particle arrived from somewhere distant. The vanishing stars are at the edge of the observable universe. The black hole sound is 240 million light-years away. Even the wow signal came from somewhere outside our immediate neighborhood. The gravitational wave background is here. It is passing through the room you are in right now, through the screen you are reading this on, through your body, through every atom of every object on this planet, through Earth itself. The waves that Nanograv detected are not waves from a distant source that happened to reach us. They are waves that fill all of space, including the space you currently occupy. Your body is at this moment being stretched and compressed by gravitational waves from merging supermassive black holes billions of light-years away. The stretching is unimaginably small, far smaller than a proton, far smaller than any scale that has any biological significance. You cannot feel it. No instrument built for human use could detect it in an individual person, but it is happening. The universe is not something you look at from the outside. You are inside it, inside its background oscillation, inside the waves that carry the accumulated history of 13 billion years of collisions and mergers and gravitational interactions across 2 trillion galaxies. We built atomic clocks. We found the most stable clocks in nature, neutron stars spinning hundreds of times per second, maintaining their rhythm for millions of years without measurable drift. We distributed those clocks across our galaxy,
monitored them for decades, and used the tiny deviations in their ticking to hear something that has been passing through everything since before our solar system existed. The detection required 50 years of pulsar timing infrastructure, decades of continuous observation, multiple independent international collaborations working in parallel, computational tools that did not exist when the oldest data in the analysis was collected. And what all of that produced, what 50 years of infrastructure and decades of observation and multiple continents of collaboration finally heard, is a hum. A deep, slow, stochastic hum that fills all of space and carries encoded within it the history of every supermassive black hole binary that has ever spiraled inward across the observable universe, and possibly the echo of inflation, and possibly the vibration of cosmic strings, and almost certainly processes and sources we have not yet identified. We have been inside this hum our entire existence as a species. We heard it for the first time in 2023. Every new way of observing the universe has revealed something that no previous observation could see. The telescope revealed that the Milky Way was one galaxy among many. Radio astronomy revealed the cosmic microwave background. X-ray astronomy revealed neutron stars and black holes in a way optical astronomy could not. Gravitational wave astronomy, beginning with LIGO in 2015, opened a new channel entirely, one that carries information no electromagnetic signal can carry, from events and epochs that light cannot reach. Pulsar timing arrays are the lowest frequency gravitational wave observatory we have yet built. They hear the slowest waves, the waves from the most massive objects on the longest timescales. They hear the universe at its most fundamental, not the brief, violent events that LIGO detects, but the background, the baseline, the permanent gravitational texture of a cosmos that has been evolving for 13 billion years. And the background is there. It was always there. We built ears large enough to hear it. And the universe, which had been making this sound since long before anything alive existed to listen, continued exactly as it always had, filling all of space with the accumulated gravitational memory of everything that has ever collided and merged and fallen together across 13 billion years of existence. Patient, pervasive, indifferent to whether anyone was listening, until something was.